We are doing applications. Here is where the word problems and the diagrams and a bit of physics and a bit of business comes into play. From here on out, it is all word problems. Good luck. One of the most important applications of derivatives is optimization. This is where we are maximizing things like areas, volumes, and profits, trying to minimize distance, costs, and time. So in solving these problems, one of the things we need to know is if we can model the function of spending, if we can model the function of area, then to maximize it, we need to know that where is the derivative zero, right? We want to find the peaks and valleys of our functions in order to be able to determine what are minimums and maximums. So in example 1, again, we're going to start off easy and get more challenging as we go, although you will find, I think, all of them challenging, which is kind of the point. Welcome to calculus. Example 1, find two positive numbers whose product is 10,000 and whose sum is a minimum. What do we know? What do we know? What do we have? Where do we start? Where did you get x and y from? Okay, let x be greater than 0, y be greater than 0. We state our assumptions. Next. We know that x times y is 10,000. Anything else? Can isolate y. 1, 2, 3, 4 zeros over x. We want our goal is for the sum of x plus y to be a minimum. What else can I do? What equation are we analyzing?
Maybe we can write y in terms of x in the equation.
In here?
Yeah.
Okay. I'm going to call the sum s.
Oh, then you take the derivative of s, right?
Oh, what an interesting thing to say in a unit where we do derivatives. Let us rewrite y in terms of x. So now we have a function s of x that is x plus 1,000 or 10,000x. I'm going to put them over common denominator if you don't mind. Maybe not. I'm just trying to think. If I were to do the derivative, I think this way would be easier, right? Because then I don't have to do the quotient rule. Yeah, let's do it this way. Okay, so when we did lessons 1, 2, and 3, our goal was to understand how to find the minimum and maximums. So the goal here is, where is it a minimum? So we want to find an x and y value that give us a minimum of this function where x times y always gives us 10,000, right? So let's analyze s prime of x. This will give me 1 minus 10,000 times x to the negative 2, or you can write it 10,000 over x squared. Either way is fine. 2, 3, 4 over x squared. And if, sorry, if you'll excuse me, that might be in thing. Okay, what would I do next? Set it to 0. Okay, do that. Okay, to find the minimums, we set our derivative to 0 and we solve for possible values of x that would make this happen. What do I do next?
Or just subtract the negative so you get positive.
10,000 over x squared must be equal to 1. So that means x must equal.
100.
Yes, good catch. Positive or negative 100, right? And for the people who are confused, what I did here is x equals positive, negative, the square root of 10,000. Okay. So now what we're going to do, what this has told us is we have two critical points. Okay. And there's going to be two ways we can test it. Either we draw a little number line and say, okay, negative 100 is here, positive 100 is here. Let us test f prime of negative 110, something on the left side. Let's test f prime of something in between 100 and 100. So let's, any number will do. You can pick one. Right? And let's test f prime of positive 110. So pick any number that's on the right side of 100. So you could do this and you could decide, is this positive or negative, positive or negative, positive or negative? And you could see where the max and mins are. Alternatively, you could take the second derivative and test f double prime. What is happening at f double prime of 100? And f double prime of negative 100. That would also tell you whether it's a max or a min. You pick the path of least resistance. What should we do?
Second.
Okay, let's do the second derivative. So we want this. So let's move this down. What is f double prime? Or I guess this is s, sorry, double prime. This would be positive 2 times 10,000 to the power x negative 3, right? So stick 100 in here. What do I get? And I'm only interested, is it positive or negative? I don't care about the actual number. Oops. Positive or negative? So this gives me a plus, which means that from this critical point, I'm about to go up. Means I have a graph that is concave up at this point. What about negative 100? It gives me a negative number, so my graph is pointing down. Therefore, this is the minimum. So we have found one of our numbers, right? Therefore, x equals positive 100. What is the other number? Is it positive 100?
Would be because x times y is.
Or you could take what y equals, divide it by your critical point, 100.
Right.
Okay, so on this graph, the two possible numbers, or the two numbers that satisfy both of the equations, or sorry, both of the requirements, is the point 100, 100. Or x equals 100, y equals 100. Either way is fine. Okay, so you can test for max and mins in multiple different ways. Pick the way that you find easiest. Sometimes taking the second derivative is easiest, and sometimes it isn't. It just depends how ugly your equation is, right? All right, let's do another one. Also, did I move too fast? Is that okay? Okay. A farmer has 2,400 feet of fencing, and he wants to fence off a rectangular field that is that borders a straight river. He does not need a fence along the river. How many sides do I need? 3, right? Because one side is the river and the other 3 sides are the fence. What are the dimensions of the field that gives me the largest area. Let's draw a picture. Here is the river. Here is my fence. Now, I could have 2 widths and a length, or I could have 2 lengths and a width. Genuinely doesn't matter how you draw this, because you can label it however you want. The math will work out the way the math will work out. So you pick how you label it. I'm going to stick with this one. What do we know? This is the picture, but using the information, let's set up something. What do we know? Right. We know how much total fencing he has, which is essentially the perimeter of the fence, right? So we know that 2W plus L is 2,400. What is my goal? Okay, goal is max area. What is area?
9 times the width.
Okay, so area is length times width. We always want to be working with a single variable. So what else could I do?
Isolate one of the variables from the other.
Isolate one of them. Pick one. Sure. Let's say that L equals 1,200 over W. So then my area is what? Something's wrong. Oh my goodness, we did this wrong. Boo. Try again.
Oh.
It's like minus.
We're plussing, we're not timesing, right?
We should think W equals to 1,200 L. But 1,200 minus, no.
No,
That would
because
not
we're
work.
adding and subtracting. We're
Yeah,
not multiplying,
yeah.
dividing. Whoa, good catch, guys. Very common, right? Because this is where we start unraveling with word problems. We got to be very careful what we're doing. Okay, cool. We caught it. All right, so what we're saying is 2,400 W minus 2W squared, right? W times L. So we're going to substitute and distribute. And we're going to do the same method that we did. In order to maximize or minimize anything, we first have to do the derivative on the critical points. So A prime is A prime 2,400 minus 4W. And then to maximize, minimize, I set this to 0. Right, so W is 2,400 over 4, which is 600. This is a critical point. This does not tell you if it is a max or min. You either have to test on the number line or you do the second derivative. What should I do? All right, let's check A double prime. A double prime is?
-4.
Ooh, not helpful.
So we have to.
So you have to check the number line.
Right.
Okay, let's check the number line. If we have a number line with 600 in the middle, what is A prime doing when it's 500? What is A prime doing when it's, I don't know, 650 or really any number? You could do like 599 and 601. That's fine too. Sure, that would make it easy. Let's do 1. And then let's do, I don't know, 650. So you're taking A prime, this equation, and you're putting 1 where the W is, and then you're putting 650. A prime of 1 is positive. Okay, so we have an increasing graph, and then 650, negative, perfect. This is a decreasing graph, so yes, that is maximum. Okay, so to maximize the fence, W must equal 600. And therefore, L equals minus, oopsie, 2 times 600. Is it 1200?
Yeah.
Perfect. We have found the dimensions. What is the area? 72. How many zeros? Count.
It's 720,000.
So the 72 is right, but how many zeros?
4.
4. 1, 2, 3, 4. 720,000. What's the units?
Square meter.
Square
Square feet.
feet. Beautiful. Okay, so again, the other part of word problems is a concluding statement, right? Or at least an answer in a box with correct units. So just pay attention to what we're looking for. Are we good? All right, next. Example 3. A cylindrical can has to be made to hold 1 liter of oil. Find the dimensions that would maximize, or whoopsie, I read that wrong already. Find the dimensions that would minimize the cost of the metal to manufacture the can. What am I minimizing?
The volume.
Try again. Surface area, right? Because the can is going to be metal. It needs 2 lids and a side, but the volume is 1 liter. Okay. For the purposes of this exercise, we are going to assume that the volume is the same ratio, like we're going to use liters as the units for volume. Does that make sense? That it's like a 1-to-1 ratio between the cubic stuff and the whatever. And you'll notice that it doesn't actually tell us any other dimensions, right? So we can set the units to what we need them to be. So we're going to pick the easiest one. We're just going to use 1. Okay. Do we know what a cylinder looks like? Okay. What dimensions do I need for a cylinder? Radius and height. Okay. Who remembers the surface area? Oh, let's do an easier one. How about we do volume? Pi r squared times height or length, depends what you label it, okay? So now, we know the volume, we know the volume equation, and we know the volume must be 1 because we are choosing to use liters as our measurement of unit, or unit of measurement, sorry. Okay? What do we want? More money. When do we want it? Now. Surface area. Remember, surface area is the sum of the areas of all the pieces of the can. What do we see on the can? 2 circles. So 2 pi r squared plus circumference times the height. 2 pi r h. Good job. Okay, so h is the height, right? And if you unravel the can, you're going to end up with a rectangle for the center, and the length of that rectangle ends up being the circumference of the can. Great remembering, that's the word. Oh. Okay, we want this to be a minimum. We want to spend as little money on the metal as possible.
But we also want to isolate the variable.
We also want to isolate variables. Thank you for volunteering your services. Which variable would you like to isolate? Pick the path of least resistance. Why did you pick H? That's a very smart choice. There's only one H. I don't have to square root. Path of least resistance, right? Okay, so we are going to isolate H. H is 1 over pi r squared. So we are going to take the surface area, make it a function of the radius, and anywhere that we see h, we are going to substitute pi r squared.
So don't pi and r cancel out on.
I sure do. So this simplifies to, okay, I'm going to stop writing SA. That's too much writing. Just A. We're going to know that this is area. I'm going to pull out a 2. Actually, no, it doesn't matter. Leave it there. 2 pi r squared plus, I'm going to write this as a negative exponent, if you don't mind, just to make the derivative easier.
So what about the 2?
Oh, yeah. Thanks. Okay, what do I do next? Oh, derive it. Can you imagine? In calculus, we are deriving. What is the derivative? 4 pi r. Lovely. Then what do I do? Set it to 0. So can I skip a step and just write it as 4 pi r equals 2 over r squared?
I didn't see complete work.
Do math. That's not if it's right.
You would not take point.
I wouldn't. That would be so mean. That's algebra. I would not take points off of not showing work on algebra. I would take points on not showing points on derivative though. Okay.
Right?
Set to 0, then do math. There you go. Okay. Skip another few steps. R equals cube root of pi by 2 or 2 over pi?
It's 1 over 2 pi.
That's 1 over 2 pi.
Y'all, you're right. Okay, are we happy with that?
Okay, I'm sorry, guys. I took
Question for the people in the room.
Do it.
Do I need a plus minus?
No.
Why not?
It's a cube root.
Cube root. I missed something.
What do you miss?
I want you to find it. I'll give you a hint.
Oh, it's a negative inside.
It's an unwritten thing that happened when I skipped all the steps. You see, sometimes life lessons just fall into your lap, guys. You're welcome. If I get this to 0, and let's,
Oh, you can factor out an R.
oh, what an idea.
Smart.
What would this simplify to?
We're getting the same thing.
Almost,
Do you do this on purpose?
maybe.
You're getting one extra.
I am getting an extra solution. What's the extra solution?
0, 0.
Almost right.
Infinity.
Why is it infinity?
Because it's a negative power.
Ah,
So now we're gonna use any amount of. Wow, so that's already not.
so this is not currently a solution because it would mean that we'd have two reasons why it's not a solution. We can't have a 0 in the denominator, and we can't have a radius of 0 because that means we don't have a can, right? However, let's suppose you have a quadratic in a different question and you don't quite catch that. That could be a solution because if that r had a positive exponent, 0 would be a legitimate solution. Yeah? Okay, life lessons. Show your work. Okay, moving on. This does not give us a legitimate solution, so we're just focused on this part here. So then r equals the cube root of 1 over 2 pi. We did end up in the same place, but I want you to catch the in-between bits, okay? Okay, this is a critical point. Looking at a prime, is it worth us doing a double prime, or should we test the number scale? Okay, remember double prime doesn't always work, yeah? So we can try it, but a double prime would be 4 pi plus 4r. That works. Nope, -3. Cool, almost missed it. Okay, so let's now test what is a double prime of this ugly thing. So on your calculator, you're going to do 4 pi plus 4 divided by cube root 1 over 2 pi. All cubed. Oh, I don't even need a calculator, guys.
Exactly.
4 pi plus 4 times 2 pi. I don't even need to know what the number is because I know it's positive, which means it's concave up. Cube root cubed. There's a cube on it. So cube root cubed cancels out. And then all of these numbers are positive. So we have a smiley face, which means this is a minimum. Hooray, we found it. So, conclusion. R is this ugly number. What is H? Go up.
Oh. This is.
It's ugly, isn't it?
Yeah.
1 over pi times the cube root of 2 pi squared. Tell me if you understood what I did there. Because it's a negative, it's in the denominator, so if I invert it, then now it's in the numerator. Here's the original for H. 1 over pi, and r squared is in the denominator, so I made it in the numerator by inverting this.
Oh, okay.
Okay, I skipped too many steps. 1 over the cube root of 1 over 2 pi squared. So this is like saying the cube root of 1 over 2 pi to the -2. So then if I invert this, that makes it positive.
Because it's a fraction.
Look, okay,
The
here's,
top and bottom
let's
are the same.
forget it. You can leave it like this. It's fine. I'm happy. We don't have to do it if it's hurting your brain. Are we okay?
Yeah.
That's it. That's all. That's it. That's all. Okay. We will do one last example for today and we'll do the rest tomorrow. Oh my gosh, this is the ugliest one. No, hold on. Will you come to class tomorrow? Because it's your grade 12s and it's pep rally day. Okay. We'll stop today. We'll stop today. It's fine.
Are you gonna take a day off?
Why would I take a day